That's what we just derived right there. The orbital radius cubed over the period squared is equal to some constant. And the third one, planet sweeps out equal area in equal time. What that means is that I got the sun sitting right here, I got a planet. As it gets closer, I'm going to make my ellipse a little bit more extreme. So the sun is here, the planet is here. As it goes around, when it gets closer to the sun, it's going to go faster. So let's say that after a month, the planet moves that far. So that's 1 month, pretending. Then, if it's closer to the sun, it has to move faster because this area and this area would be equal. Not necessarily the way I drew it, but that's what he's claiming in the third one, is that it sweeps out the equal amount of area in the equal amount of time. And that makes some sense. So let's say that I have a planet here traveling in that direction. So this is the direction of the velocity. I have a sun over here. What is the direction of the force on the planet from the sun? What is the direction of the force on the planet from the sun?
Towards the sun?
Yeah. So it's being pulled, so the force is in this direction. What is the direction of the acceleration of the planet? You're pointing in the same direction as the velocity?
Yeah.
No. Think of Newton's second law. F equals ma. What's the relationship between the direction of the force and the direction of the acceleration?
Opposites?
I think someone said something.
Are they opposite?
No,
They're the same?
they have to be the same. There are only two vectors in the problem. They're on each side of an equal sign. The directions have to be the same. So the acceleration is that way. Now, if the acceleration is perpendicular to the velocity, it's going to travel in a circle. But that acceleration is not perpendicular. Which means that part of this acceleration, because remember, the acceleration, change in velocity over change in time. Part of that acceleration is going to get that velocity to speed up, because part of that acceleration is in this direction here. And part of that acceleration is perpendicular, which will get it to curve. So when the planet is here, part of that force is causing it to speed up. It's going to get faster and faster until it gets to this point. It goes whipping around, and then it's going to start to slow down. And then it'll speed up, and then it'll slow down, and then it'll speed up. So it travels faster when it gets closer to the sun, and less fast as it gets farther away. Well, similar to so many things. I throw this in the marker. It gets slower the farther it gets away from the planet. It gets faster the closer it gets to the planet. This last one here is just conservation of angular momentum. And we can demonstrate the exact same principle without using planets. I do need a swivel chair. I'm guessing most of you have seen people demonstrating conservation of angular momentum on TV at some point in your life. In this model, I am the sun, which is what my parents called me. These are the planets, 2 for balance. And what happens when these get closer to the sun? Yes, they do. It's the exact same principle as what we're working on right here. I don't do that so much at my age, so I will stop on that one. Now, I will claim, I will speculate, that I'm glad Kepler was dead by the time Newton came along. Kepler had no clue about why this is true. This is based purely upon astronomy and observations. Spent 40 years of his life doing this. At this point, if you've had calculus, you can actually derive this in an afternoon. So just imagine you spend 40 years of your life on something, you meet Newton in a bar, and they talk about what they're doing. Kepler explains to Newton that he's looking at planetary motion, and Newton does, got an afternoon, I can show you how to do it. So, I hadn't done that routine with this group yet, had I? Is that the first time? First time? Okay. So, Kepler gets claimed, well, what he did was absolutely amazing, however, it is not, it's just an application of Newton's laws. Questions before we start on chapter 10? I've got the prop for this one. I do. Have I used this with this group yet? Okay. No, wait a second. All right, so what I'm going to do is set this thing up. I'm gonna bring it down so I can actually see what I'm doing. This ball has a hole in it so that it can slip over the edge here. And this one has a hole also, but all right, so I'm not using the holes. This is going to push on the solid side of it. So when I trip this right here, there's this rod right here. There's a spring attached to it. This rod is going to shoot that way. And because of inertial properties, this will basically stay where it is and should fall relatively straight down. This ball right here is going to get shot that way. Let's give myself a little bit more room for shooting it that way. Don't think it's going to go too far, but we might end up redoing this. So when I hit the lever, which one is going to hit the table first? I got the one that's falling roughly straight down and the one that's being shot that way.
The one going straight down.
Straight down? Anyone else? Going for shot that way? You know, let's do physics by democracy. So there's the one that's straight down and then the one that's shot that way. I guess there's tie, and then let's assume they will not burst into flames on the way down. Have an opinion, even if it's just based purely upon gut or guess. The one being shot off to the right. So I'm seeing 3 there. The one dropping straight down. 4 there. And tie? Manolo, I don't think you voted yet. Good morning.
Okay.
Which one's going to hit first? The one that falls straight down, the one that's shot, or will they hit at the same time?
Say same time.
Same time? Here we go. Let's make sure that they start at the same level. I'm glad that didn't break. Which one hit first?
Same time? Was it same time?
It should have been roughly the same time. There was a big ting there. Let's see if we can do that again with. Oh, there we go. I'm just constantly hitting stuff. Hopefully you heard that the crash happened about the same time. This one's traveling farther, definitely, but it's also traveling faster. But so if I want to know how fast this is going, well, I could just figure out how long it takes to fall that distance. As a matter of fact, we can do that. And of course, I need more than a meter. There's one over there. I assume that's the one that fell straight down. We'll get that in a second. All right, so it is falling about 1.16 meters. That's the distance that this one fell. It started at rest, flash back to chapter 3, for something that's falling, the distance is equal to 1/2 GT squared. One of the last formulas from chapter 3. So the distance, 1.16 meters, is equal to 1/2 times the acceleration due to gravity, which is
1.8.
meters per second squared times time squared. So the math problem we're working with here, 1.16 is equal to 4.9 t squared. That's the math problem. So divide by 4.9. So T squared is whatever that is. About 0.25.
So where did the 4.9 come from?
Oh, 1/2 times 9.8.
Whatever.
Sorry, I jumped through that quickly. Uh, 0.24. And so the time .47. Four nine seconds. So it takes about a half second for that thing to fall. And now it'd be really nice to figure out what happened to it. Rachel, I know there are tables in the way, but you didn't happen to see where it went.
I think it's right there by the tire.
Oh, there we go. Thank you. So we can figure out how fast it's projected because once it's launched, what are all the forces acting on it once it is in the air?
Weight,
Anything else?
force, or no,
Just wait.
just weight.
Yeah, just wait. In which direction is weight acting on it?
No.
So the acceleration is downwards. There's no acceleration horizontally because the force is down. So the force is in that direction. So part of the force is causing it to curve, and part of the force is causing it to get faster. And so if I know how fast, so if I know the distance that it travels this way, I can figure out how fast it was shot initially. So let's set that up again. I don't care about the one that's falling, I just wonder about the projection. And basically I want to know how far horizontally does it go, how far that way. And I'm just going to do an observation here. It hit right there. I need to know the point at which it was launched. It was launched at that point right there. And it's a crude estimate, and it looks like it's about 1.1 meters. So from the vertical, I know how long it's in the air. Horizontally, it goes 1.10 meters. And this is, again, no acceleration horizontally, it's all vertical. So horizontally, horizontal, and this was vertical. Distance equals speed times time, or displacement equals velocity times time. It's just traveled in one direction horizontally. It's equal to v times 0.49. And so my speed is 1.10 meters divided by 0.49 seconds. That's 2 point something
2.24
units.
meters.
So this thing is being shot at a little more than 2 meters a second. Let's bring in some other stuff that we've done. If I shoot it straight up in the air at I just erased it. So it was 2.24 meters per second. The other stuff that I just erased, anybody need me to write that up again? So 2.24 meters per second upwards, how high up will it go? Well, a couple ways of doing it. Let's do energy though. Once it is launched, the only force acting on it, again, is just the weight, a conservative force. Energy is conserved. E initial equals E final. This is my initial kinetic plus my initial potential. It's equal to my final kinetic plus my final potential. Here we go. I know you're psyched for it. What's the formula for kinetic energy?
1
a little bit of an echo, but you're getting there. So it's V initial squared plus, what's the potential energy associated with weight?
NG?
The potential energy.
Oh.
It's not energy.
That's the force. Look for the potential energy formula. Unless I missed something.
MGH?
Yeah, there we go, MGH. MGH, initial. MGH, final. What can we get rid of? We have this thing that's being shot up into the air.
Mass? Mass?
Yeah, the mass, actually. In every term, we can get rid of it. We could multiply by 2, but then we'd have a 2 attached to this, so we have VI squared plus 2GHI equals VF squared plus 2GHF. If we multiplied everything by 2, those fractions had it coming. We can get rid of, we could divide by G. I'm not sure that really gets us, helps us out at all. Are any of these terms equal to 0?
Initial velocity?
No, we assume that this is the initial right there. Unlike the ski problem.
Final height?
You want final height 0? Is that what you said, final height? Why is that 0?
Because wouldn't it touch the ground?
Final height, I want to know how high up it goes. So the problem starts just after it's launched to whatever the highest point is.
Is there an initial height?
Then why is the initial height 0?
Oh, never mind. Is it starting after it goes?
So we're gonna basically rotate it that way and launch it. So it's gonna launch from this height right here. I'm curious to find out if this will actually work on this. I might have to tilt it some just so that it doesn't fall off.
If that's the starting, if that is the starting point, then it would be 0, right?
Why is it 0?
Because it's the starting point.
No, what was that?
Because it's the starting point.
That's not the reason why.
No?
It's not moving. It's not moving at the moment.
Officially, it is moving at that point. We're gonna,
So
that's how fast it's going. You've forgotten about your own personal powers.
No, because I said that.
Yes, that's why. HI equals 0, because Gary said so. We could have gone with Taylor's suggestion to make the final height 0. That would have been perfectly fine too, because Taylor said so. You have to pick H is equal to 0 somewhere. And we have one other thing that we can, that will be 0.
final velocity,
Why?
because it'll stop.
Yeah, That's the point, that's the peak. It stops at the peak and before it starts coming back down. So that will be 0 because final speed is 0 at the peak. So we're left with our initial speed squared is equal to 2gh final. We're trying to predict how high up it's going to go. So our h final is vi squared over 2g. We know what vi is, so we did those calculations well enough. G, we pretty much know what that is, so we can now make a prediction. And let's find out how well this actually works. The ball is right, it ended up in here. Yeah, we'll find out what happens. Let's see, how easy is this gonna fall off? Gonna tilt this slightly, give it a little bit more stability. All right, Taylor, you've got the best view here. Fix that in just a second. All right, I assume you can see the meter stick well enough? I guess potentially, Raphael, you've got the second best view. All right, so the initial, well, we'll get the initial height in just a second. Just want to know how high up this thing goes. What number did it go to?
I can't tell you the exact number, but down, right there.
All right. That's 79 centimeters, the 70 side. So 79 centimeter mark. That's not the final height because we need to subtract out the initial height. Oh, well, we can actually, because it was on it like that, the initial height would be around there, which is around 53 centimeters. So that's based upon this being 0 right there, but we want to make this 0, so we just basically subtract 53, so that becomes 26 centimeters. So our prediction is 2.24 squared over 2 times 9.8. That's our prediction. And experimentally, it went up 0.26 meters. So that's our experimental result. That was bad. Well, a lot closer than I was expecting.
0.256.
0.256? Huh. Can't believe, Taylor, you were 4 millimeters off. Physics demonstrations usually don't come out that close. You might not appreciate it, but I'm shocked. I'm assuming there's no errors at all. Sorry, Cheyenne, I guess you've got the worst, you're the farthest away. Do you need me to read anything for you?
Oh, no, you're good.
All right, and Joanna, I guess you have the slanted angle.
I can see.
Okay. That, in essence, what we just did then, is what you'll be doing on Friday's lab. Except you'll use the projectile launcher, so you don't have to delicately balance the ball there. You'll shoot it out horizontally. You figure out you'll do it 10 times, see how far out it goes. From that, you'll figure out the initial speed. Then you'll shoot it straight up predict how high it will go versus the experimental. Questions? All right, so going with our projectile launching here. So I've got, let's say I have this mound of dirt and I have a cannon right on top here, and I'm gonna shoot a cannonball. Assume that the cannon is stable enough that they're not worried about recoil. If I shoot a cannonball, what's the ball gonna do? Hand gestures would work also. Okay,
They go curve down.
yeah, so if I shot it faster, what would happen?
Go farther.
Yeah. And faster? All right, I hope this is not a strange concept, that the faster it's shot out, the farther it will go. Now let's take into the fact that the Earth is not flat. You know, at some point the Earth will start to curve. Now it still holds true that the faster you shoot it, the farther it will go. If we change our scale here, at some point, it's going to go even farther, not because it's being shot faster, but because the Earth is curving away from it. It's like the projectile is chasing the Earth, but the Earth is running away. So at some point, I should be able to shoot it fast enough that it should go all the way around. When the curve of the arc, when the curve of the projectile happens to match the curvature of the Earth. And we have a special name for if we can shoot it that fast. And what is that special name? There's several of them. What's the projectile called when you shoot it that fast? And if you're someplace without light pollution, you can actually see these things. It's not a strange word. Well, I'm sure all of you have heard it before.